Hi, hello, ib3 students. Next lesson about fluids in motion. Yesterday we were talking about Bernoulli effect, so about motion of fluids. Today I'm going to present some applications of this effect, but at the beginning let's do short revision of two equations which will be very useful today. First is known as a continuity equation. Continuity equation. Okay, which says that cross-sectional area through which fluid flows multiplied times speed of the fluid is constant. What does it mean? It means that when area changes, then speed also changes. Bigger the area is, smaller the speed, and vice versa. And second, known as Bernoulli equation. Bernoulli equation. Okay, is about flow, is something we can derive by using a typical law of conservation of energy. So part related with dynamic fluid, part related with static fluid is plus pressure of the fluid is constant. So it means that when pressure changes or height on which fluid is placed, then velocity or speed must be changed. Okay, so this is something we did yesterday, and today a few applications of this. Okay, I hope that you are prepared to the lesson. Book, notebook, pen, pencil, ruler, maybe some colors. Today we'll be drawing. Calculator is not necessary today. We'll be not calculating. I'm going to derive 2-3 equations without calculations, without numbers. Okay. So write a topic, applications of Bernoulli equation, or applications of Bernoulli law. Okay, applications. Okay, so first application is something, let's name it, flow out of a container. Let's imagine that you have a container which is filled by a fluid, okay? And there is a small opening at the bottom of the container. Yeah, so we can imagine something like this. This is our container, and here let's name this point B, or level B, small opening. Container is filled by liquid, and let's focus on point A, which is at the surface. Okay, so let's imagine that here we have a liquid of density ρ, and our arbitrary level or level of reference is here. So this is our something like a 0. Okay, and let's imagine that the height difference between point A, surface of the fluid, at point B, this small opening, is h, and we have a stream line from A to B. Okay, and this liquid escapes the container at B. Okay, and the idea is that we want to calculate the speed of the fluid flowing out of a container. Okay, of course we have two states or 2 points, A, and let's assume that at A we have atmospheric pressure P, and speed of the fluid is 0. So speed is equal to 0. And we know that atmospheric pressure. Okay, and what do we know at B? Okay, at B we know that its liquid fluid escapes the container with unknown speed, and we know that pressure is also atmospheric because here the pressure outside is the same as here. Okay, so also atmospheric pressure. And we can write Bernoulli equation for this problem. Bernoulli equation says that half of density of the liquid times squared speed times rho g height difference plus pressure must be constant. Okay, so it means that this at A must be equal to this at B. So half of rho times speed at A, which is equal to 0, plus rho g times the height of A due to our reference level, which is equal to h, plus P, this atmospheric, this is for A, is equal to half of rho speed at B, which is unknown, plus rho g times height due to our level, which is equal to 0, plus P. So left hand of this equation refers to point A, right hand of this equation refers to point B. We can cross something. P is the same here and here. We know that this is equal to 0, so we have 0 plus rho gh is equal to half of rho v squared plus 0. Okay, so density of liquid is the same here and here, so we can cross it. Finally, obtaining equation gh is equal to half of v squared, or v is equal to gh. You see, we've obtained exactly the same result as using a typical law of conservation of energy. Let's imagine that we have an object at A which falls, okay, and at A it has a potential energy mgh due to the reference level, and at B it has potential energy which is equal to 0, but it moves, so it has kinetic energy half of mv squared. So we can obtain the same result by using law of conservation of energy or simple energy transformations. Here we've obtained this by using a Bernoulli equation about flow of the liquid. Okay? Please copy this. This problem is known as a flow out of a container. Okay? Okay. Bullet point number 2, the most challenging, I'm going to present at the end. Okay, let's name this spray, typical spray, a fragrance spray, yeah? So let's imagine that you have a typical spray, and I will try to describe how it works. We have something like squeeze bulb, okay, which is usually made up of rubber, okay, which is connected with a kind of pipe which changes thickness. Okay, this narrow part of the pipe is connected with the hose which is immersed in the liquid. Let me try to draw it. Oh, nice flask. Okay, a blue liquid which fills this container. And of course we have something like a nozzle here through which liquid or droplets of liquid in the form of spray can escape. Here. Okay, so how it works? Let's look. First of all, we have to squeeze this squeezing bulb. Squeeze bulb. Squeeze bulb. Okay, so what happens if bulb is squeezed? Squeezing the bulb creates a force of air through the tube. Okay, so here we have an air which moves through the tube. Okay, this air enters this narrow part of the tube here. So what happens here? Air enters this narrow part, so it changes velocity. What happens? Speed of the air here increases. If speed of the air increases, then what happens with pressure? Pressure, of course, decreases. So pressure here decreases. This low pressure region makes a liquid to flow up from the flask directly into this directly into this stream of air. Okay, so next point we can write that liquid is drawn up tube. Okay, bar pressure difference. Okay, and finally, what happens? This liquid enters the stream of air and in the form of small droplets escapes the flask. Okay, so here droplets or drops or liquid is emitted from the nozzle. Okay, so again, one by one. First, squeezing the bulb, and squeezing the bulb makes a movement of air in the pipe. This moving air changes velocity because the pipe is thinner and thinner. Change in velocity, increase in velocity results in decrease in pressure, which means that this low pressure is able to move liquid from the flask directly into the stream of the air when in the form of the droplets it is emitted from the nozzle. Okay, so here you have how typical spray works. Now, maybe let's take a pitot tube. So this is a tube which measures the speed of the aircraft. Okay, the name of this is a pitot tube. Okay, it consists of two parts. The very thin pipe, okay, with opening at the end here, and another pipe which is around with opening here and here. Oh, like this. So we have pipe inside the pipe. Okay, let's imagine this usually is installed at the front of the plane, at the front of the plane. Okay, so when a plane travels to the left, then what happens with air? Direction of airflow is to the right. Okay, so this is direction of airflow. Okay, and here we have a small part called impact opening. Okay, so what happens inside this tube? I'm going to make a color. Okay, inside this tube we have a total pressure. Okay, the static pressure and this pressure related with this impact. Yes, so in this red tube we have a total pressure of PT. But of course we have also another openings here called static pressure opening. Which means that inside this tube, this here and here, we have a static pressure. Let's name the static pressure PS. Okay? We have two regions. In the impact opening and inside we have a total pressure. Okay? And these holes, static pressure openings, measure static pressure without movement. Okay? So what is the difference between total pressure and static pressure? Difference between total pressure and static pressure is of course dynamic pressure. So we can write that dynamic pressure is a difference between total and static. Of course these two pressures are measured. Yeah, we can measure the pressure in the red tube and we can measure the pressure in the violet tube. But what is the dynamic pressure? Due to the Bernoulli equation, dynamic pressure is half of rho v squared. So we can write that half of rho v squared is a difference between total pressure and static pressure. So finally we can measure the speed of airflow. So practically we can calculate the air speed. So practically we can calculate the speed of the vehicle, the speed of the plane, because this is the square root of 2 times difference between total and static divided by density of air. Okay, so again, by using Bernoulli equation, we can measure the speed of air flow. Okay, please copy this. Okay, so next application, let's take airfoil. So the cross-section area of typical wing. Okay, aerofoil or airfoil, aerofoil or airfoil. Okay, so what is this aerofoil? What is the shape? Aerofoil has a shape like this. Okay, let's imagine that our plane travels to the left. So what is the airflow? Airflow is from left to right. So we can create few lines above. Like here. One above, next above. And one more above. Okay, and few lines below. Like this. Or this. Okay, so let's look on these lines. Here, the stream lines are closer together above this airfoil. Okay, so here lines are closer. Okay, what does it mean? If lines are closer, it means that the air above must travel with higher speed, v, let's name it 1, than below. Lines are farther, so speed is less. Okay, so practically we have a speed difference. The air above the airfoil travels faster than below. Remember, if speed is bigger, then what happens with pressure? Then pressure is smaller. If speed is smaller, then pressure is bigger. So what happens? Above the airfoil we have a region of small pressure, and below the airfoil we have a region of high pressure. Okay? So this pressure difference creates a lift force which is directed from high pressure to low pressure. So this airfoil experiences a force, a lift force, which is directed up. Yes, and when this lift force is equal to the gravitational force acting on the airfoil, then airfoil doesn't experience any resultant force in vertical direction, which means that it's able to fly. Okay, due to the first Newton's law of motion, it doesn't accelerate and doesn't up and doesn't accelerate down. So again, we can use Bernoulli equation, okay, to estimate this, to calculate this. So remember, shape of the airfoil creates a different movement of air, different speed of air above the airfoil than below. So pressure difference, and pressure difference results in force which acts up on the airfoil. Okay? And so this is fourth application of our Bernoulli equation. So please copy this with, of course, a kind of comment. And finally, the most challenging, something which is known as a Venturi tube. Okay, what is a Venturi tube? Venturi tube can be used to calculate the rate of flow of fluid, okay, by measurement of pressure difference between two different cross-sectional areas of a pipe. Let me show it. So let's imagine that you have something like this tube, which looks like this. So change of the diameter of the tube. This part is connected with another. Like this. Here we have another element, something like U-shaped pipe, which connects this very, very narrow part of the tube with this thick part of the tube. Okay, and let's identify two points. Point A of cross-sectional area A, which is here. So this is point A, and cross-sectional area of this point is, not of the point, the cross-sectional area of the tube is A, and another point B, and cross-sectional area at point B, let's state that it's B, okay? Here we have, so area A and area B. Okay, inside we have a moving fluid here. If it enters the narrow part of the tube, then it changes the speed. Okay, so here we have also the same fluid, and here also with another speed. Okay, but we have to focus on 2 points. Point A, which is here, point B, which is here. Okay, I hope that you know that when this air enters the region B, okay, then it must move faster. If it must move faster, then the pressure decreases. So speed at B is bigger than speed at A, so pressure at B is less than pressure at A. If pressure at B is less than pressure at A, then another element here. Let's imagine that inside you have another liquid, like mercury. Okay, if pressure at B is less than at A, then this liquid moves towards B. And let's imagine that height difference of this liquid is H, or delta H. Oof, I hope that it's all something like preparation to our equation. Let's one more. This liquid, this red one, has a density of ρ2, okay? And this liquid which flows has a density of ρ. Okay, so liquid which flows has a density of ρ. And one more assumption, these 2 points, point A and point B, are at the same level, are at the same height. Okay? So let's look. Let's focus on this part. What is a pressure difference? The pressure difference, delta P, is equal difference between pressure at point A, which is higher, and at point B, which is lower, because again, in area B at point B, speed of the fluid is bigger. So delta P is difference between PA and PB, and it is of course a hydrostatic pressure of this red liquid. So you can write that this is hydrostatic pressure of this red liquid, which is given by density of this liquid, ρ2, G, times height difference. Okay? So this is first description of hydrostatic pressure. Okay, I'm going to write 2 equations. Bernoulli equation and continuity equation. So let's start with continuity equation. Continuity equation says that cross-sectional area times speed is constant. What does it mean? it means that speed times area here must be equal to speed times area here. So we can write that area A times speed of the fluid at A must be equal to area B times speed of the fluid at B, or in other words, I'm going to use this for link speed A, speed B in the form of VB is equal to VA times A over B. Okay, this is our first equation. Oh, practically second, because one is here, one is here. Okay, and now Bernoulli equation. Okay, Bernoulli equation says that dynamic pressure half of rho v squared plus static pressure plus pressure of the fluid is constant. Okay, what does it mean? It means that this part at point A must be the same as this part at point B, but remember, in our case z is equal to 0 because A and B points are located at the same height. Okay, so I'm going to write this in the form of A to the left and B to the right. So what do we have the left part of this equation? This is half of density of fluid times speed of fluid at A squared plus density of fluid times gravitational acceleration times z, which is equal to 0 because point A has the same level as point B, okay, plus static pressure at point A. Static pressure at point A is this. We have additional pressure at point A from this red liquid. So ρ2 times G times delta H. Okay, so this is our point A. I'm going to move it a little. Okay, and point B, we have exactly the same. Half of rho VB squared plus rho G0, because point B is at the same level as point A, and the pressure is equal to 0 because we've used this extra pressure the left hand of the equation. Okay, so we can write half of rho VA squared plus rho 2G delta H is equal to half of rho VB squared, and now we know that VB is equal to VA times cross-sectional area of A over cross-sectional area of B. So we have half of rho VA squared plus rho 2G delta H is equal to half of rho VA squared A squared over B squared. Oof, so we can write this in the form of we are interested what VA is. So half of rho VA squared, and now we have A squared over B squared minus 1, this is the same, is equal to rho 2G delta H. Finally, VA is equal to the square root of, numerator is 2 times density of red liquid times gravitational acceleration times height difference of left liquid in the left and the right part, divided by cross-sectional area of A over cross-sectional area of B squared minus 1 divided by density of fluid which flows. What for? Let's look. We can calculate the speed of the fluid, okay, by measurement only the delta H, this. Okay, when fluid here in the tube travels with different speed, then delta H changes. And knowledge about delta H allows us to calculate speed of the fluid in the tube. Oof. So I finished. I was talking about 5 applications: about venturi tube, about flow out of the container, about typical spray, about airfoil, and about a pitot tube. The most challenging venturi tube is at the end, and this is something like the best application of Bernoulli equation. Okay, so thank you for watching. Next lesson probably about viscosity, yeah, because this is next problem related with fluid. So we'll be talking about viscosity and about types of flow, laminar flow, turbulent flow. We'll be talking about Reynolds number, etc., etc. So again, thank you for watching. If you have any comments, suggestions, please write this as a comment in Google Classroom. Learn physics, stay at home, and see you. Bye.